Hello physics students. Welcome to the Centripetal Force Lab. So as always, at this point, you should have printed out pages 2 through 6 of the lab sheets included in Google Classroom Stream. You'll be recording all your data on these sheets and doing all your calculations, as well as answering the questions at the end. Again, as always, you don't have to print out this first sheet because it's instructions unless you want to, because you feel it'd be more convenient to have a hard copy next to you. Now, what are we going to be doing in this experiment? What we're going to be doing is we are going to be testing this equation, okay? Equation we learned in class for circular motion. What that means is we're going to have to get something, first of all, moving in circular motion. Then we're going to have to determine its mass, determine its speed, and determine its radius of orbit. We plug those in and calculate, and we'll get some number of newtons based on the equation of circular motion, and then we'll compare it to some number of newtons as a known value and do a percent error and see how close this equation gets. So that's the goal of the experiment. So what is it that we're going to put into circular motion? What we have, or what I have, is this little device. I call it a whirler, and essentially what it is, it's going to have metal blocks hanging on the end here. You'll be able to control how much metal you put on here. A hollow plastic tube that this string can slide through with a little clip on it for reference, and a rubber stopper at the end. The rubber stopper is what we're going to swing into circular motion. So what I'm going to do is take this and get it going over my head until I have a stable orbit. Oops. Oh, you know why? Ha! I have 700 grams, not 300. I was thinking, boy, that is really fast. All right, let's go 300 grams. Yeah. There we are. That's better. Okay, so then I'm just going to spin this over my head and get it into a stable orbit. Now, there is a centripetal force. Those metal blocks are pulling the stopper in. If I stop spinning it, see what happens? The metal blocks pull the stopper in, right? See that? So that's the inward centripetal force coming from these hanging metal blocks. So what I need to do, that's going to be the accepted value, but what I need to do is get the mass, the speed, and the radius of the thing in circular orbit. So I'm going to bring the camera closer and show you how I can get the mass and the radius. So let me reconfigure. So the thing going in circular motion is the stopper, and so I need its mass. What I'm going to do is take this whirler and put it, the stopper on the balance like this, and I get 11.8 grams. I don't know if you could see that. And I'm not holding the string up. I'm letting it sag like that. Okay, it's actually 11.9. So I'm going to write that in for the mass of the stopper. 11.9 grams. But a few things. You're going to get your own mass of the stopper from the Google Stream. The other thing is, all masses in physics are not in grams. They're in some other value. So this has to be converted. In fact, you don't even have to write this down. Write the converted value for the mass over here. All right, so that was the mass of the stopper. And next, we're going to have to determine the radius of orbit. That's basically what procedure step 3 says over here. And I'm not going to read it. But what I want to do is make this orbit radius 40 centimeters. To set that up, there's a little clip over here, like from a backpack. And I could slide it up and down. When I let it go, there's like a spring that clamps onto this string, and it's going to be basically like a marker. If I want this radius of the stopper to be 40 centimeters, I do not put the clip 40 centimeters away. The reason why is because watch what happens when I start spinning this. So that clip's 40 centimeters away. When I go like this and start spinning this, the radius now is only like 20-something centimeters. So I need to make the stopper here and the top of the tube 40 centimeters away. So let's see, I guess I'll stretch this like this. So let me move this. 40 centimeters away is the top of the tube. And there it is. Now what I need to do is put this not up against the plastic tube because I don't want any forces on the stopper from this plastic clip. It's only to mark the radius. So when I'm spinning like this is about 1 centimeter away from the bottom of the tube. And when I spin, I'm going to spin it so that it spins around and the radius is 40, and I'll know it's 40 if this gap stays about 1 centimeter as I'm spinning. So now I've fixed the radius to 40 centimeters. So again, that has to be in meters. I got my mass, my radius. The next thing is the speed. So let me configure the camera and show you how I'm going to determine the speed. So I have the mass and the radius. I now need to figure out the speed. How am I going to do that? I'm going to use a stopwatch. So what I'm going to do is take this, spin it over my head. By the way, I didn't mention this, but this is why I'm wearing the safety glasses, because the stopper is going to go quite fast, and I don't want to, if I mess up, damage my eye. So you would be wearing safety glasses in class. What I'm going to do is get a stable orbit going. Now, if you notice, if I spin this too slow, this drops. If I spin too fast, this is going to go up against the plastic tube. So what I want to do is spin it so that it stays about 1 centimeter below. As I explained, that's going to ensure that the radius is 40 centimeters. And I'm going to time this orbit. You see it's very fast, and it'd be hard to see one orbit. So the easiest thing is to time 10 orbits and then divide by 10 for one orbit. It lessens the error. So I'm going to do it all the spinning and the timing because I'm here by myself. I'm going to say ready, set, go. 1, 2, 3. Okay, so I got 3.04. Maybe I'll try another one and see how that goes. I have to time my hand 10 times while I'm timing. Ready, set, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 2.91. So somewhere around there, maybe I'll keep the first one, 3.04 seconds. Again, you are going to get your own value from the Google stream, just like the mass of the stopper. So I put that in here. Okay, now I'm going to put 3.04. However, that is not the correct time. It tells us, just like I had to convert the mass of the stopper to kilograms, I have to convert this to the time for one orbit. That's the time for 10 orbits. So you need to figure out from that time what the time is for one orbit and put it right there from the data that I gave you for 10 orbits, okay? So the next thing you're going to have to do is in box number 6, you have to calculate the speed of the stopper from this time and the radius. So V equals a formula, numbers plugged in, and then an answer. No centripetal force equation, no mv squared over r. You're just thinking about this time and figuring out a distance for the orbit of a 40 centimeter radius, but in meters. Calculate the speed. Go ahead and do that now. The next thing you're going to have to do is over here, you're going to have to calculate the centripetal force based on this speed. So there's an equation for circular motion. I showed it to you earlier. You need to find it on your reference table or your notes. I won't show it to you again. Calculate what the centripetal force is in newtons. Now keep in mind, there's mass in the equation. Think very carefully of what mass you're putting in. Are you putting in the mass of the metal blocks or the mass of the stopper to get the force of the thing in circular motion? So think about that, plug in your numbers and calculate the centripetal force. Do that now. Okay, and then over here, it says to calculate the accepted value of the centripetal force. To help you see what that is, again, I'll go show you this device. So the stopper, as we could see, is going to get pulled toward the top of this tube, right? So it does get pulled toward the top of this tube. There is an inward force. What made that inward force? Some people say the string. All right, yeah, the string. But why? What pulled on the string to make that inward force? All right, looking here. All right, what pulled on that stopper, pulled it in? There's a formula for the force of that thing. There's a word for it, right? When these things pull down, why do they pull down? What's that force that we call that, or what do we call that force? There's a formula for it on the reference table. So go ahead and calculate that force. And I'm not going to put a subscript here because I'll give away the answer of what that force is. But you need to figure out what the accepted value is based on what I just showed you. Go ahead and calculate that now. And then the last thing, percent error between these two values. Go ahead and calculate that now. Okay, so now we move on to the next trial. So that is the next page, step 12. Before you whirl the object, so we're going to keep the, no, I'm on step 10, sorry. Repeat steps 3 through 9, but change the radius to 50 centimeters. So what I'm going to do is bring the camera closer to show you how I could change the radius to 50 centimeters. So let me do that now. So what I need to do is now follow that procedure I used for fixing the radius of 40 centimeters and do it again to fix the radius of orbit at 50 centimeters. So what I'm going to do is I'm going to slide this out of the way for now, and I'm going to put the stopper at 0, centered at 0, and the top of the tube should be 50 centimeters away from the stopper. And now what I want to do is move this clip about 1 centimeter away from the bottom of the tube. And there it is. I now have a radius. If I spin with a gap like this, the radius of orbit will be 50 centimeters. So I have the radius, the mass I still have. I have all the masses I need in the lab. You need to figure out which one to use. But I need to figure out the speed to test this FC equation. So let me reconfigure the camera so that I could figure out that speed. All right, I'm ready for trial 2. So again, I'm going to do the same thing. I'm going to get this spinning, and I'm going to figure out the speed of this with a stopwatch and some calculations. So let me get the orbit in a stable situation here. There it is. Okay, so ready, set, go. Okay, so I got 3.02 seconds. Let me try again. Ready, set, go. Okay, 2.84. Maybe I'll stick with the 2.84. Again, you are going to get your own value in the Google Stream, but yeah. So I put 2.84 seconds here. But again, the value out of the Google Stream is not the correct value. We want the time for 1 revolution, and this is the time for 10. So you actually have to convert this somehow for the time for 1 revolution. So that's for you to figure out. All right, step 6, you're repeating the same set of calculations. So over here, step 6, if you read the procedure, it says calculate the speed from this stopwatch data and the radius over here, and then get an answer over here in meters per second. Has to be in meters per second. Step 7, calculate the centripetal force. There's an equation. I showed it to you, but of course it's also in your notes. Remember, there's a mass in this formula. Once again, think very careful about what mass you're plugging into this formula. There are two masses in the lab, the metal blocks on the bottom or the rubber stopper up above. What do you plug in, mass of the stopper or the mass of the metal blocks? Think about what's in circular motion. And then get centripetal force as some number of newtons over here. Then, step 8, we want to get the accepted value of the centripetal force. Once again, I showed you this before, but I'll show it to you again. This stopper is definitely pulled in. When I let this go, that stopper is pulled in, as you can see. So what created that inward pull? There's also a name for that force that created that inward pull. F subscript, what is it? Formula, so on and so forth, calculate. Do that now. And then percent error here, do that there. So go ahead and do that now. Okay, so we're going on to the next step in the lab. Procedure step 11, which is part 2, trial 1. We're going to keep the radius 50 centimeters, but change the hanging mass to 250. And then we're going to do something a little bit different. Let me get the lab sheets here. What we're going to do is step 12 says, before you whirl the object, calculate the centripetal force on the object. Hint, do not use FC equation. Instead, determine the gravitational pull on the metal hanging masses. So right here, no mv squared over r, the gravitational pull on the metal blocks. Go ahead and calculate that now. Keep in mind it's 250 grams. Make that calculation now. Step 13. From the FC determined in the previous step, determine the speed of the stopper's orbit. Not from the stopwatch. I haven't spun it yet, so I don't have a time. So from the circular motion, calculate the speed. We've got the newtons already. Use the formula to solve backwards and get the speed. Go ahead and do that now. Okay, step 14. From the speed you calculated, determine the accepted time of orbit for one revolution. So from this speed you calculated, eventually solve for time. So go ahead and do that now. Now step 15. Whirl the stopper under these conditions and measure the time for 10 revolutions. Determine and record the measured time for one revolution. So I'm going to time it 10 times again. And then I'm going to figure out the time for one. So I need 250, so I'm going to put 250 grams down here, changing the hanging mass. Uh-oh. All right, now I lost both masses. Let me reset the stopwatch, put it in my pocket, ready to go. I lost the mass again. All right. I hope you're not laughing at me. Or if you're laughing, it's all in good fun, right? So, okay, here we go. Stable orbit. Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 3.86. I'll try another one. go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 3.79. So pretty close. Maybe I think the 3.79 was a better one. I'll write that one down. Again, you are writing your own time down. So 3.79. But again, that was for 10 revolutions. You've got to convert for 1 revolution. So go ahead and get the time from the Google stream and write your answer there. Go ahead and do that now. And then the last thing, you've got a time here, you've got a time here, you're going to calculate a percent error there. So go ahead and do that now. Okay, one more trial, part 2, trial 2. So let's take a look. Repeat the steps 12 through 16, but this time alter the radius to 35 centimeters while keeping the hanging mass constant. So I got to change the radius to 35 centimeters. So I'll bring the camera closer so you could see how that's done. Okay, so we changed the radius to 35 centimeters. What do we do now? So we are repeating this block of instructions, which means we haven't timed it yet over here, right? Time has not been determined, but in step 12, where before you whirl the object, calculate the centripetal force on the object. Hint, do not use FC equation, instead determine the gravitational pull on the hanging metal masses. So the hanging metal masses, we're going to determine the gravitational pull, and then over here we're going to have some number of newtons. So go ahead and do that calculation now. All right, step 13. Step 13, from FC, the FC determined the previous step, determine the speed of the stopper's orbit. So we are going to determine the speed, but not from distance over time. Again, we don't have a time yet. So we're going to use this formula with this value, and we're going to calculate speed. Keep in mind we're plugging in mass again. Again, think carefully about what mass you plug into the circular motion formula. What object's going in circular motion, and plug in the mass accordingly. Okay, out of the two choices, the hanging metal blocks or the stopper, what mass goes into the circular motion equation. So go ahead and calculate that speed now. Okay, step 14. From the speed you calculate, determine the accepted time of orbit for 1 revolution. So from this number, you're going to start with that speed, and then you're going to calculate what the time is to go around. So go ahead and make that calculation now. Now, step 15, finally, we're going to time this. So let me go over here, get ready, stopwatch in the pocket. Let's see. All right, so I am ready to start spinning and create a stable orbit. Okay, there we are. So, ready, set, go. Okay, 2.63 is what I got. I'll try again. I mean 3.50. Whoa, way different. Let's try again. Okay. .01. 3.02. All right, well, I guess I'll go with 3.01. Again, you're going to get your own value from the Google stream, 3.01. But again, that's what you get from the Google stream, whatever value it is, but you don't use that one. You want the time for 1 revolution. So go ahead and get that number now. And then finally, a percent error between this time and this time that you do right here. So go ahead and do that now. Okay, so now we are on to the questions. So question 1, in part 1, the radius changed from 40 to 50 centimeters while the hanging weight remained the same. Explain why this would increase the speed of orbit. And then here's something it's telling you. State and use the equation for centripetal force. That means you have to write out the formula right when you start. And then you tell me, based on the formula, how changing the radius, increasing it, what does that do to the speed? So go ahead and do that now. Step number 2, or question number 2. Going from part 1 to part 2, you decrease the mass hanging on the device while keeping the radius constant. What would this change do to the speed of the orbit? State and use the equation. Again, you have to start by writing out the equation for centripetal force. And then explain, where does the mass hanging, where does it fit in that formula? And what is making it smaller do to the speed of the orbit? So go ahead and answer that now. And then number 3 is the concept that gets to the heart of circular motion. When asked, most people explain that the stopper remains at a stable orbit because it is in equilibrium. The inward force on the stopper provided by the string is balanced by the outward centrifugal force. The net effect is that the stopper does not rush in toward the top of the tube as a result of the string tension. This logic is flawed because the centrifugal force does not exist. Come up with the correct logic by answering the following questions. Is the stopper in equilibrium? If you don't know what that means, go back to the force unit or look it up online. What does force equilibrium mean? If yes, there's a typo here. What are the forces that balance? If no, how can the stopper be accelerating even though the speed remains constant? So answer that question now. Okay, so that was the Centripetal Force Lab. I hope you enjoyed it as much as I did. So again, take photos of all your calculations and all the answers to your questions, submit them in the Google Stream under this assignment, and I'll see you in the next video.